Tá ligado? Ok, bem-vindo ao seminário GADEPs.
English.
Então, hoje o Wodson vai falar sobre a foliação em característica P em inglês.
Bem, eu vou falar inglês, mas meu inglês é muito bom. Eu espero que seja entendível. Thank you, Hossein, for the invitation. So, my plan here is to try to give some surveys of the things that I did in my PhD. That's about the codimension one foliations that I did under the supervision of George. And give you some examples of how you can use this theory to study problems of holomorphic foliations. So let's start. So here's a plan of my talk. You'll be divided in 4 parts. And the part 1 is just introduction. I will define the basic objects here. In the part 2, I will talk about derivations and foliations in characteristic P. I will define P-closed and P-closed foliations and some properties. In the part 3, I will specialize to the codimension 1 foliations in positive characteristics. In the part 4, I will give examples of problems that we can prove by using characteristic P. So from FP to C. So let's start with introduction. So K will denote algebraically closed field of characteristic P, can be 0 in this first part. X will denote a smooth algebraic variety, defined of K, of dimension at least 2. And the codimension Q foliation, F, on X is given by an covariant subsheaf of the tangent sheaf of rank Jimmy X minus Q that has the following properties. So this subsheaf is closed by the Lie brackets, and the quotient is free torsion. And this is the definition of foliation, and plus this condition. The condition that there is free torsion, and the singular set is defined with the set of points show that this quotient is not free as a X modulo. So in this talk, by foliation, I mean codimension 1 foliation. In that case, we have 2 line bundles associated to the F, that is the normal sheaf, the normal bundle, and the conormal bundle. The normal sheaf is defined with the double dual of this quotient. And the conormal sheaf is a set of 1 forms that is vanishing when we contract with elements of the tangent sheaf, the foliation. And you can see that this is isomorph to the dual of the normal sheaf. And from this inclusion, we get a non-trivial section of this bundle here that has its properties here. This is an integrability condition that corresponds to the fact that the tangent subsheaf is closed by the Lie bracket. And the singular set that is pointed that vanishes this 1 form. And we ask that it has codimension at least 2. That corresponds to the condition that the quotient is free torsion. Torsion free, yeah, thank you. So we have the definition 2 for codimension 1 foliation with normal bundle N that is given by a non-trivial section, omega, which has its properties that we saw in the previous slide. When X is a projective space, we can write explicit equations for this, polynomial equations, and we have the notion for degree, that is number for the tangents of a generic line Pn with the foliation. That is algebraically is just this. So we take a line in Pn, and we take a 1 form, define the foliation, and we contract, and we restrict it to this line, and degree is the degree of the 0 locus of this form here. In particular, we get this. So explicitly, we can write the polynomial equations for the foliations. So using the Euler-Zeit sequence, the projective space, and we multiply by O d plus 2, we conclude that the codimension 1 foliation Pn is given by the homogeneous one form in the affine space an plus 1, in this way, that has these properties. So A0, An are homogeneous of a degree d plus 1 with the condition in the singular locus. And with sigma having these properties here. So this is a projective condition and this is integrability condition. By integrabilidade, the condition of the fact that the foliation, the one form is integrable means that we have a lot of equations if you write the relation. And I will denote the space of a codimension 1 foliation by this set here. We are looking for the projective one forms that satisfy the integrability condition and the condition of the singular set. And classical problem here is to describe the irreducible components of this space when the K is a complex field. Example of foliations, we have this simplest case here. So this is a foliation P2 of degree 1 that has these curves as solutions, or invariant curves. And we have the general case of this, that we take a lot of polynomials, and we take elements of the field that has this condition, the residual condition, and we consider this one form. In this, you can check that this defines a foliation Pn of degree this. And this is called the logarithm foliation of type D1 to dr. And you can check that these IP surfaces are invariant by the foliation. So when we work in the projective plane, we can define the foliation by the vector fields, homogeneous vector fields. So in that sense, the foliation for degree d is given by the homogeneous vector fields of degree d in A3, with this condition that the divergence of this vector field is 0. The equivalence of these notions is given by this result that you can find in the journal book. That there is a bijection between the set of projective one forms in 3 of degree d plus 1 and homogeneous vector fields with divergence 0 of degree d.
So you need, for that, you need this condition of the first one.
Yeah. Yeah, because they have vast implication. We need to divide both for this constant here. So here we have an example. So if you have this foliation here, we write this d omega in this way, and the homogeneous vector fields with the divergence 0 is given by this LMN. Example, you take the simplest case, degree 1, and you apply this formula here, and you arrive at here. Okay, this was introduction. Now I'll move to derivation and foliation characteristic P. So here is a algebraically closed field, and if take R K domain, a K derivation of this ring is a map which satisfies the following. For every constant and for every functions, f and g, we have this formula here. If you take a j natural number, it denoted by the j iteration of this operator, we have this formula here. In particular, if k has characteristic p, we conclude that the p satisfies the Leibniz formula here. In particular, the p is on derivation. So if you have characteristic p, you can construct derivation by just taking the p powers of the derivation. So some properties here, if you take a function in d1, d2, two derivations of this ring, then we have these formulas here. For the p power of the sum can be written as sum of the p powers plus something here, where this thing here is only a polynomial in D1, D2, and we have this another formula here.
So sorry, what do you mean by E polynomial?
So it's a polynomial that can be written as combinations of the quotient
Okay.
of D1, D2.
Okay, so it's
Combinations
a
of
polynomial
these
in-
things.
It's a polynomial in
Like-
the combination.
Yeah,
Okay.
thing like that. So I'll talk about the closed foliation. So we take a foliation in small algebraic variety X, defined of
I'm confused with your previous formula. Why you wrote as a sum? Why you wrote as a sum of different polynomials? And exactly p minus 1 of them.
this
Not
here,
just one polynomial. The first formula.
the first. Sorry, I don't understand that.
No, you wrote sum of p minus 1 polynomials there, right?
Yeah,
Isn't it a polynomial?
I don't. Maybe there is something is wrong here.
And also, I don't think it's a Lie polynomial in D1 bracket D2. It's just an iterated bracket, right?
Yeah,
So it's D1 and D2. So here you give the impression that you are raising the bracket to a power, and that's not what you're doing.
okay. No. hmm
And this formula is yours, or it's the Jacobson, right?
It's Jacobson formula. Yeah. But the point here is, if you start with the foliation, if you take a TF, you take a V1, V2. Now I need to define what is a preclosed first. So let's move to you take a foliation in smooth algebraic variety, defined of K, and we say that the foliation is preclosed if this subshift is closed by the p powers. You take a derivation that is tangent to the foliation. The p power is inside of the tangent sheaf of the foliation. The previous formula implies that if you are working with the closed foliation, if you take V1, V2 here, then V1 plus V2 is inside into F. So because we are writing to the V1 plus V2 as a V1P plus V2P plus something that is inside of the foliation, because the foliation is closed by the Lie brackets. That's the point. Okay, I explain this later.
Maybe this S-jota means that the depths of the Lie bracket. This one means just one Lie bracket. This two means you are using a Lie bracket of the Lie bracket.
Yeah.
And then so on until. So this means that at most you have P minus 1 Lie bracket of the Lie bracket of the Lie bracket. So
Yeah, think like. Okay, this is preclosed foliations. So the preclosed foliation, the version in positive characterization for the class of holomorphic foliation that has meromorphic first integral. In particular, we have this result, which say that in codimension 1, the foliation is preclosed if and only if there are infinitely many F invariant IMPA surfaces. So here's an example, the simplest example. So we take the foliation for the defined by this one form in A2, and you can check that the F is preclosed if and only if this constant here is an element of the field Fp. Here's the proof. It's not hard to see. You just compose this vector field p times, and we check that this vector field is tangent to the foliation if and only if this constant is the element of the field. But we have some analogies, but some objects behave differently. So we have this result by Jorge. We'd say that if you take a foliation P2 and suppose that you have this condition degree, then F has invariant algebraic curve. By a result of Jono-Lobo, foliation defined over C, the picture is different. I mean, we can construct for every D foliations that has no algebraic solutions. And in characteristic P, with some conditions, we can check that the Jono-Lobo foliation of degree D has a unique algebraic solution. Okay, this was a derivation in characteristic P and foliation. Now we'll move to the codimension one foliations, a positive characteristic. For that, I will define the Cartier operator first. So here's the thing: we take K algebraically closed field of characteristic P, R on local regular K domain, which is a localization of a K domain of finite type, like this. The regular functions of the variety atom point on the fixed point. And we take T1 to TR on regular system of parameters of this ring, the generator for the maximal ideal of the ring. From these elements here, we get a basis for this modulo of differentials. The ring is on free as a IMPA modulo with base given by this all monomials of this type here. T1, A1 times TR, AR, this condition here. We have closed forms, we have exact forms, and we have obstruction. First homology group. We consider this RP modulo. It's defined in this way. And there is a proposition which says that for every closed one form, we can express as a sum of two forms with the first is exact form and the second form lives here in this modulo. And the Cartier operator is just a map. We take close to one form and project with some corrections to the second factor that lives here. We omit P and we omit this term here. And you get this map. And we can define this operator as in more intrinsic terms in this way here, as inverse of this isomorphism here. It is the isomorphism here. We can check in this book here. There's no result. And we have this fundamental formula, which says that for every close to one form in V derivations, we have this. The contraction with this, with the CP, 2p power is equal to this contraction of a VP with the one form plus this term here. This is Cartier.
Yeah, this is the Cartier.
Yep. Okay. So we have the properties of this operator. So he's additive, he's bilinear, is zero in exact forms, and we have this property here. We omit this term, and he fixed logarithm forms for any local sections f sigma 1, sigma 2.
So you are evaluating on holomorphic things like arithmetic is, the definition can be extended to this.
to the meromorphic continuum. So we'll talk about now about the non-P-closed foliations in the P-distribution. So X will denote algebraic variety of dimension 2, defined over K, again. In F, a codimension 1 foliation, non-P-closed on X. And we have this result. A lot of people here, Cevolins, Neto, Lorre, Pereira, Tuzé, which say that the foliation can be defined by closed meromorphic one form. So you take a foliation that is not P-closed. In particular, we have a vector field that is tangent to the foliation, show that the P power is not tangent to the foliation, so it's not zero. If you consider this one form here, we conclude that this form is zero, that it's closed.
This is B to the P or this?
F to P minus 1.
Like F equal to IVP or something?
This is wrong, eh? No, F is equal to E. I'm sorry. This is not zero. There's a P power here. The foliation is not P-closed. So we have a vector field that is tangent to the foliation. Show that the P power is not the subshift. So you take a omega, the closed one form defined the foliation that exists by this result, and consider the subshift of the tangent shift defined by this way, in this way. We are looking for the vector field tangent to the foliation that is tangent to the Cartier of this one form.
So, what do you mean by a rational vector field? It's
So you're looking for the
the coefficients are rational.
yeah, rational functions, not holomorphic.
Okay.
So we have this TCF, and you can check by the properties of this operator that TCF is independent of the choice of this one form, and is also saturated subshift of the X. So defines a distribution of subdistribution for the foliation. And this is the P distribution associated to the foliation that's not P-closed foliation.
Dimension 1, so omega is
Yeah, for dimension 1. The fundamental formula implies that in dimension 2, we don't have this subshift. Because for every tangent shift, for every tangent vector field that is tangent to the foliation, we have this. This is not zero, but the tangent shift has rank 1. But this is just a disk by the fundamental formula, so this is not zero. So we consider this morphism of sets shifts, which associate V to the VP.
So there is intuition behind this P distribution.
Hmm?
There is some intuition to.
The name?
What's the intuition to understand this P distribution? There's some.
So are the vector fields such that the P power are still tangent to the foliation? So we know that there is one vector field which is not, he's assuming that the foliation is not P-closed. So there is one vector field such that the P power is not tangent to the foliation. And this P distribution are the vector fields such that the P power are tangent to the foliation.
Okay, so this is the kind of
Say the this again.
part of the P closeness.
It's the, it's not P-closed because it, yeah, you can say like that, but it's not necessarily because, right? It's a subsheet such that the diff power.
Is it far from because?
No, it's not because of the foliation. Just saying
I
that
know.
since we are in codimension 1, the obstruction to P-closeness is rank 1. So the map that measures the P-closeness has a kernel, and this is this thing. So this was explains exactly that in the last slide.
Yeah. So the percurvature morphism associated to these foliations is just this map. We send this element here to this element here. And the foliation is closed if and only if this map is 0. F star is just the Frobenius map, that is identity and the topological space and the p power and the functions. So we have the curvature morphism here, and we have this result here, which says that the kernel of this map here is just a pullback by Frobenius of this sheaf, TCF. Let me put the TCF here. And there is an effective divisor, show that this sequence is exact in codimension 1. That is exact outside the closed subset of codimension 2. So we will call this divisor as a p-divisor associated to the foliation, but it's not p-closed. And we have this property here, which says that if you have a foliation that is not p-closed, and if you have an irreducible hypersurface in X, then this hypersurface is invariant if the hypersurface is invariant in them, we have this. If you're looking for the order of this hypersurface in the divisor, this is not 0. And reciprocally, if you have this condition here, then it is F invariant. In some sense, the p-divisor takes every invariant hypersurface of the foliation.
This delta F is the same as this peak determinant. This delta F is the same as the defined peak determinant some other in one of your first articles.
No, has nothing to do. Go back to the definition. So delta F, if you want, is the following. Locally, you take one form, define the foliation, and you take in a vector field transverse to this distribution DCF, but tangent to the foliation. And now you just contract omega with the if power of this vector field. You get delta F. You get the equation for delta F. That's what this equation says. Delta F is the contraction of omega with the if power of a vector field transverse to DCF.
Yeah.
So this is completely intrinsic. It does not depend on a choice of linear system. This thing with big determinant depends on the choice of a linear system. This is intrinsic. Depends on nothing.
Yeah, well, the distribution intrinsic.
It's intrinsically attached to the foliation. It's a divisor intrinsically attached to the foliation. Both delta F and DCF are intrinsically attached to the foliation. There are no choices involved.
So by taking the determinant of the exact sequence, we have this formula here, where this is a canonical bundle of the foliation F, and the omega CF is the canonical bundle of the distribution. In particular, if you work in the projective space, we have this formula here. So here I give you an example. So you take a foliation P2 given by this, and we write the omega in this way, and take the vector field that is tangent to the foliation of division 0. And the p divisor in this case is just the contraction of the p power for this vector field with the one form here. In that case, this divisor has degree p times d minus 1 plus t plus 2. Yeah, it's p closed if this divisor is 0.
Still, we are using that the p does not divide the degree plus 1 or plus 2. This is the prime.
Yeah.
Yeah, it's written there. The second.
Here.
Ah, okay.
Yep.
But you don't need that. Right?
For the definition of delta f.
Any vector field will do the job. He just chose one. He's doing that to be able to choose one which has
Division 0.
divergence
Yeah.
0. But he could choose another.
Yep. So another example, the simplest case, we have this foliation of degree 1, P2. We take the vector field, construct in that way. By iteration, we have this. The equation for the p divisor is just the contraction here, and we arrive at here. And the foliation is p close or not depends on this element here, if it's not prime field or not. So here we have a properties here. We take a foliation Pn, and assuming that the characteristic does not divide the degree of the normal bundle, then we can check that f admits an invariant IMPA surface. We just looking for degree of the p divisor. So we assuming that f is not p closed. We have this condition here. So this implies that degree is not 0 mod p. So we have a factor in this divisor. With multiplicity does not divide p. It's not divisible by p for p. So we get this and get to the solution. And I don't know if it's possible to remove this condition. And I think I found an example here. So if you consider this example here, you can check that this example does not have an algebraic invariant surface. The degree here is degree 2, that is equal to the characteristic of this field. But in P2, I don't know examples. So we have a corollary here that in the projective space of a characteristic P, any non-p-closed foliation for degree D has invariant algebraic hypersurface of a degree less than or equal to this constant here.
This was the degree of the
Yeah. And the divisor should be a P in the P divisor.
But one important thing is that in dimension 3 or higher, the degree of delta f is not determined by f. You have an upper bound. It's at most f, but can be smaller.
Yeah.
Depends on the degree of this TCF. That's one formula that we showed before.
Yeah.
In dimension 2, it is determined because TCF is the zero foliations. The degree of TCF in the circumstances determined for surface.
The problem here is that I put in the projective plan, but we can ask in this in projective space, in characteristic P, how many solution can f have? So reminding you this result, that f is p closed if and only if has infinitely many solutions. And what you can say about no p closed foliations. So I did some work in the Jonolo case. So the Jonolo foliation is defined by this projective 1 form here. And we have this result. If you assume some arithmetic conditions here, then the Jonolo foliation for degree 2 has irreducible p-divisor. In particular, we have just one solution in characteristic P. In the proof, we use in particular automorphism of the general foliation that provenience of the characteristic 0. And this fact that if you have an automorphism of the foliation, then the p-divisor is invariant. I mean, the pullback is the same as the p-divisor. So in that condition, we can conclude that the generic foliation for degree 2 in the projective plan has irreducible p-divisor. In particular, has a unique algebraic solution. And for degree bigger than 2, we have the result here that gives you a structure of the p-divisor for the general foliation. But we have some conditions in the degree and the characteristic. So if you have this condition here, we can conclude that the general foliation has an irreducible p-divisor, or the p-divisor is just this. We'd say irreducible of degree PL plus D plus 2, and R is not invariant. R is not invariant. As a consequence, we have this. So the general foliation has a unique algebraic solution in this case. This table just shows that you can have these two cases, irreducible or we have the p power in the p-divisor. Or we can have
That's just the case of the theorem,
the previous theorem, yeah, this one.
Can you explain the table?
Yeah, exactly. A little bit.
So the table here, we have a degree of the foliation. Here we have the number of the singularities of the foliation. We have a degree of the curve which appears in the p-divisor when the p-divisor is this way, reducible. And L is the degree. It's related to the degree of C. The degree of C is PL plus T plus 2. And R is the divisor that is not invariant by the foliation.
So the table depends on P equal to 5.
P5, yeah, P5. P is fixed P5, VD is bounded by 100.
And R is always the product of three lines.
Yeah. But I don't understand why this, we have this behavior here. And for this case here, we have the divisor is irreducible. And for the remaining cases, the foliation is closed.
So all the numbers are equal to 1 or 2 modified, all the b's.
Yeah, we need some conditions. I think the previous slide here. We need some conditions in the prime here.
And they are all equal to, except for 2, they are equal to -1 modified.
Yeah.
And you don't know the other
I don't.
numbers, you can what's that?
I don't know the behavior. Yeah.
Why you didn't include 11 in your list? Why 11 doesn't appear above or below?
11. I think because it's closed.
Oh, in the other case?
Yeah. Just check the list and I put every case.
So most of them are closed.
Yeah. But for instance, I don't understand why we always have this here. Maybe something related to the automorphism of the general foliation, but I don't know.
And C also might have some big genus of this C curve.
Yeah.
Okay, C, okay, of course, this is C is in P2, so it's genus defined.
No, it's very single. Not clear what the genus is. We believe that
Okay.
that is extremely
Okay.
single.
Hmm. Yep.
Now we can
Okay. Now we are going to the last part, that is reduction mod P and how to lift. So reduction mod P, I'll talk about the foliation Pn because everything is more simple. So we have equations, explicit equations. We take a codimension 1 foliation Pn of degree D, defined by this projective 1 form, E0, E1, I missed it with 0 here. Elements of this polynomial ring. So I take ZF, definitely generate Z algebra, that we get by putting all the coefficients in the inverses, which appears in the coefficients of A0 to AN. Here we have example. So we take a foliation P2 given by the simplest case, so for some element of the field. Then the algebra associated is just this. And for the general foliation, we have all coefficients here are integer, so that we have this ring.
So the algebra is not associated to the foliation, but to the one form.
Yeah, we take a one representant, one element that defines the foliation, and take the algebra associated to the one form. And we have this fact, for every maximal ideal of this algebra, the residual field is finite, in particular has characteristic P. So we have a way to construct foliation characteristic P, starting from characteristic 0. So we denote by the omega P, the one form of the Fp that we get by reducing mod P all these coefficients, and we obtain a zero element of this guy here. And this guy determines a foliation Pn. And the foliation determined by this one form is denoted by Fp, and we call the reduction mod P of F. Natural question. So suppose that we have abstract property P that holds for Fp for infinitely many primes, or almost all primes P. What we can say about F? Yeah, just technical things. So infinitely many primes, I mean primes in some dense subset of this topological space here, set of maximal ideals. And the most of primes, I mean primes in some non-empty open subset of the topological space here. So when the algebra is Z, these notions are the usual notions. So infinitely many or almost all primes. We avoid the finite number. So the property P can be the existence of the Fp invariant type surface, or can be the property that the foliation is P closed, or can be the property that F has irreducible or reduced P divisor. Here we have an example. So you suppose that we have a foliation Pn, and suppose that Fp has invariant hypersurface of a degree less than D for most of primes P.
And D is not the degree of F.
No. D, black D is just a degree of the hypersurface, the bound.
So
Of,
it's a number.
yeah. Then F has invariant hypersurface of a degree less than D. So here's the idea of the proof. So you look for the set of foliation Pn that have invariant hypersurface of a degree bounded by D, black D, I missed black here. And you check that this algebraic variety of defined of K. And we have a general fact which say that this is not empty if and only if this is not empty for almost a prime P.
By the way, at the beginning, to define the Z algebra, you inverted the coefficients also. You need really this one, invert also the coefficients of the one form. For example, if a Z
Because of the
of
problem is that
minus
you
one-
can have things like this. So if you reduce mod 2, you get 0. I just avoid this if I invert the number.
But you are going to get a full set.
Yeah.
You don't need to. I think that there will be differences also.
I just try to avoid
The
this.
primes will be changed, and those which are not so good. But at the end,
The prime is not a well-defined concept.
yeah, of course. It depends on the model.
In the model, so it's not that bad.
Okay. So the goal is the reduction model piece to use this technique to study more foliations. I will give you examples. So we have this example here. If we start with non-decretion foliation in P2, defined by this one form here, and you take a prime that satisfies this condition here, you can check that if this device is irreducible, then the F has no algebraic solution. Here's the idea of the proof. So you suppose that you have a variant curve. We can assume that it's defined by, we have a coefficient in Z. And we have a decarnation bound for non-decretion foliation, which says this. And reduce the variant curve, we have a bound. And by reducing modulo P and using reducibility of this divisor, we get a contradiction. And the question here, I don't know how to remove this condition, non-decritical. So
this can be applied for dual foliation, just
yeah,
some class of them, not all of them, because it was irreducible.
yeah, we can apply. Just one prime, you get information to the foliation. But I don't know how to remove this. Yeah. And here another result about the reducible components that we proved in my thesis that this map defines a reducible component of this space here. So you're looking for maps from P3 to P1 times P1 of degree 1. The coordinates are homogeneous polynomials of degree 1. And here denotes the space of foliation P1 times P1 that has canonical divisor of degree D1, D2. And you take the pullback, and you get a foliation here in P3 of degree D that is given by this. And this map defines the reducible components of the space here. The topics in the proof include the structure of the P divisor for generic foliation P1, P1, improving the analog theorem in characteristic P, and lift it to characteristic 0. So the main question that the main point here is that we have good foliations in P1, P1. With good means by having P divisor with good properties, in the sense that in the sense of this problem. So you take a smooth algebraic surface. The problem is what you can say about the P divisor for generic foliation, F. Is it true that most foliation on X have a reducible P divisor, reducible? And how to construct foliations with good P divisor? Good in the sense, irreducible or reduced. In this direction, we have this theorem. So we'd say that the generic foliation of degree D has a reduced P divisor. And another theorem would say that the generic foliation P1 times P1 with canonical divisor in this way has reduced the P divisor. So this theorem was important to prove this theorem here, because I used this factor to prove this theorem in characteristic P and then lift it to the characteristic 0. Yeah, I will discuss the proofs of the theorem, so I'll stop here. Thank you. que outra codimensão, não cheguei a olhar não. Se for codimensão 2, codimensão 3. Eu não sei se dá para definir um análogo do P-divisor também, não.
It's this last theorem in the degree 2 just recovers one component.
This theorem here.
Yeah, in this I'll see this servo classification. This recovers. Or there is no component corresponding to the okay, D1 equal D2 equal. Oh, so it applies it from starting from D equal to 3 on. No. Okay.
Now D is at least 3.
Okay, it's bigger than 3. Okay. Maybe let me. So in maybe talking about the component in let me say formulate in this way. This can one use also this thing to classify the component just in characteristic P? Space of foliation just in characteristic P.
Yeah, we have a special foliation characteristic P
Uh-huh.
that gives you irreducible components.
It's a project that we have been trying to do since he finished his PhD thesis. There is
Yeah.
everything written down essentially, but we haven't finished yet.
But there is a strange phenomenon which happens in
Yes,
the
for
classification.
small p, general principles implies that for P large, the description is the same. It's just what
Yeah.
the right set, defining over Z, and so eventually you get a bijection between irreducible components in one side and the other, and the things are
Yeah.
the same. But when the characteristic is small compared to the degree, different things happen. For instance, for degree 0, the only characteristic where things are different are characteristic 2. Degree 1, I think the only place that the things are different are characteristic 3. And things, but eventually everything's the same.
Okay. Any question from online audience? Tá bom, se não tem mais pergunta, mais uma vez, obrigado, Wodson.
Thank you.
Mas você está ainda com as perguntas?
Wodson, tem uma parte do artigo relativa